Hello everyone. So here we are going to continue the discussion in thermodynamics. So we have completed the first law of thermodynamics, steady flow energy equation, and the steady flow devices. In this session, we will be discussing on second law of thermodynamics. Second law of thermodynamics. So we have seen zeroth law of thermodynamics and first law of thermodynamics. So here today we will be discussing on second law of thermodynamics. So when coming to the difference between first and second law, we know that first law states that the energy is conserved quantitatively. So quantity of the energy remains the constant, but it can be transformed from one form to another. That is one way of stating first law of thermodynamics. Now coming to the second law, it states that qualitatively, that is whenever the energy transformation is taking place from one form to another, energy is continuously deteriorated in quality. Quality of the energy is continuously degraded. So we have studied many processes: constant pressure, constant volume, constant temperature, constant enthalpy, constant entropy, right? And steady flow process, unsteady flow process, uniform, non-uniform. So any such process cannot take place unless it satisfies both the laws, first as well as second law. So that much importance is there for the laws of thermodynamics, especially first and second law of thermodynamics, for any process to happen. So these are the differences in a nutshell. You can see here the first law places no restriction on the direction of a process. It just states the quantity of the energy is conserved. Okay, but coming to the second law, the processes occur only in a certain direction, but not in the reverse direction. That means the process will happen only in the direction where the quality of the energy is deteriorated. Quality of the energy cannot be increased when the system undergoes a process. That is not possible. So in short, the second law asserts that energy has quality as well as quantity. Energy has quantity as well as quality. Now certain points, terminology you need to understand before going to discuss in detail about second law of thermodynamics and the systems based on second law of thermodynamics. The first such term is thermal energy reservoir, or TER. It is a hypothetical body with a relatively large thermal energy capacity. So what is thermal energy capacity? You know that what specific heat is, right? So when the specific heat is multiplied with the mass of the system, it is termed as thermal energy capacity, the heat retaining capacity for a specific mass of a body, that is thermal energy capacity. So thermal energy reservoir is a hypothetical body with a large thermal energy capacity that can supply or absorb finite amounts of energy in the form of heat, finite amount of energy in the form of heat without undergoing any change in temperature. So whenever such hypothetical body absorbs or rejects energy in the form of heat, there won't be any temperature change. Such a body is called thermal energy reservoir. So there are two kinds of thermal energy reservoirs, TER: source as well as sink. Source is a thermal energy reservoir which can supply enormous amount of energy without undergoing any temperature change. On the other hand, a sink is a hypothetical body which can absorb, accept enormous amount of energy without changing its temperature. The examples: oceans, lakes, and obviously atmospheric air. This could accept enormous amount of energy every day. You know that oceans and atmospheric air or lakes or rivers are absorbing enormous amount of energy from the industries, and as a result of so much of processes happening in the atmosphere, still the temperature, more or less the average temperature, remains the same for a period of time. Now the second important terminology in learning second law of thermodynamics is heat engines. Heat engines. So obviously you know that what is engine, right? So heat engine is an engine which works on the input heat. It is often used to represent work producing devices that do not operate in a thermodynamic cycle. So it will be an open cycle. Continuously the working fluid will be replenished. So the devices such as internal combustion engines or IC engines, which operates in a mechanical cycle but not in a thermodynamic cycle. I hope you know the difference between thermodynamic and mechanical cycle in detail. So please understand the difference, but not in a thermodynamic cycle, since the working fluid does not undergo a complete cycle. As I mentioned, there will be replenishment at the end of each cycle in the case of mechanical cycle, replenishment of the working fluid. But in the case of thermodynamic cycle, it will be a closed cycle. The same working fluid, the same amount of working fluid will be undergoing the different transformations or different processes continuously. But in the case of mechanical cycle, the working fluid will be given into the first component of the system. It will undergo certain process and will come back to the initial condition, but at the initial condition it will be expelled out of the engine or the cycle, and the fresh charge or the working fluid will be given in the first process again. So for example, in the case of an internal combustion engine, the exhaust gases, instead of being cooled to the initial temperature, they will be purged out and replaced by fresh air fuel mixture. Now the third important term to understand, to learn, is the thermal efficiency. The thermal efficiency is the index of performance of a work producing device. It is the index of performance of any work producing device, such as engines. It is defined as a ratio of the net work output or the desired result. Net work output could be desired result to the heat input. The ratio of these two is termed as thermal efficiency, and it is denoted by the Greek letter eta with the subscript Th. Th stands for thermal. So let us see what will be the mathematical expression of thermal efficiency. Let us derive the thermal efficiency of a heat engine. So the desired result always in the case of a heat engine will be work done. So what will be the case of work absorbing devices? Still there are efficiency for compressors or pumps that we will discuss later. There also the efficiency is there. Okay, so thermal efficiency is specifically applied for a heat engine where the input is thermal energy or heat. So thermal efficiency is always less than 1 or less than 100%. It cannot be more than 100% or 1. Okay, it will be between 0 and 1 or 0 and 100%. So it is a ratio of desired result or net work output in the case of heat engine to the heat input. So the net work output for a cycle is the work that is going out of the system minus work that is coming into the system. Now let us apply the first law. We are applying first law. This efficiency is also known as first law efficiency. So when we apply the first law to the cycle heat engine, you know that net heat transfer is equal to net work transfer, right? Because for a cyclic process, the change in internal energy will be zero. We have seen this already in the previous sessions when we have discussed about the first law of thermodynamics. So the net heat transfer is equal to net work transfer, or W net out is equal to Q in minus Q out. So we can write the net work out divided by Q in, or net work output is equivalent to the net heat transfer, that is Q in minus Q out. More amount of heat will be given, a certain portion of that heat will be utilized to produce work, and the remaining will be rejected as Q out, right? So Q in minus Q out divided by Q in, or we can write it as thermal efficiency of a heat engine as 1 minus Q out by Q in. For example, let us quickly see an example of a steam power plant produces 50 megawatts of network, megawatts, 10 to the power 6 watts of network, while burning fuel to produce 150 megawatts of heat energy at the high temperature. So fuel is giving 150 megawatts of heat to the steam turbine power plant, and the power plant produces 50 megawatts of network. So out of 150 megawatts of net heat input, the power plant produces 50 megawatts of network. So you need to determine the cycle efficiency. It's quite simple, right? Out of 150, only 50 megawatts is converted to work. So efficiency will be 33%. 50 by 150. And how much heat is rejected to the sink would also be calculated using this expression. You know that W net out is equal to Q in minus Q out, or QH minus QL. So QH is given. How much heat is given to the power plant is given as 150. So QL could be easily calculated as 100. Just the difference. I hope the concept is clear, the thermal efficiency concept. Now let us see the two different statements of second law of thermodynamics, Kelvin-Planck statement and Clausius statement. So now consider a heat engine here, which is continuously producing work output by absorbing, accepting heat from a high temperature thermal energy reservoir. So there is no heat rejection. The entire heat absorbed is converted to work output. So such a heat engine is impossible. That is the Kelvin-Planck statement. So no heat engine can convert the entire thermal energy into mechanical work output. There should be some heat rejection. Otherwise, it will become a perpetual motion machine of second kind. That is Kelvin-Planck statement. Now coming to the Clausius statement, see here. So this is a reversible heat engine, the refrigerator, which transfers thermal energy from a low temperature reservoir to high temperature reservoir without the help of any external work. That is quite impossible as per Clausius statement. So no refrigerator can transfer thermal energy from a low temperature to high temperature without any work input. The opposite is true. The transfer of thermal energy from high temperature reservoir to low temperature reservoir is quite possible because the heat flows from high temperature to low temperature. Okay, but the reverse, if you want to make it true happen, there should be some work input. That is Clausius statement. Fine. I hope the lesson is clear. If you have any clarifications, doubts, please comment below. Please share with your friends. We will continue the second law of thermodynamics in the coming session with the definition and the detailed discussion on refrigerator and heat pump. Till then, goodbye. Thank you.